We are going to do parallel circuits today. And one of the things I want y'all to remember is all the things that we learned in the beginning about how current is affected by the resistance and the voltage and the path, okay, the current path. That's a big thing. So let me just talk about the basic concept of a parallel circuit first. If I've got two resistors in parallel, let's say this one is 50 ohms and this one is 100 ohms, right? So one of the rules about finding total resistance in a parallel circuit is the total resistance will always be lower than any resistor in this circuit. It'll always be lower. I want to explain why. If I ask you to tell me the total resistance of this circuit, what would you normally do in a series circuit? You just add them together, right? Well, that's not the case in here, in this one, because there's two separate paths for current to flow. So what I want to do, real quick, let me show you the formula that you'll use to find total resistance in a parallel circuit, and it's called product over sum. Product over sum, R1 times R2, our product is divided by R1 plus R2. All right? So this would be 50 times 100. I'll go ahead and tell you the answer to this. It's going to come out to 75. I'm going to say. All right, 50 times 100. So that's going to be what, 5,000 plus, and divided by 50 plus 100. So that's going to be 5,000 over 150. So what's 5,000 divided by 150?
75.
75. So RT is 75 ohms. Now, the rule I just told you, the total resistance will be lower than any of the resistors, and it is. Wait a minute. It ain't 75. My fault. It ain't gonna be 75. It's gonna be 25. But do 5,000 divided by 150. What's that come out to be? It ain't gonna be 25 either.
It is going to be 33.3.
33.3, okay? I went against my own rule there, okay? The total is lower than any of the resistors. It's lower than R1, it's 33.3. All right. All right, remember this formula right here. So, I'm gonna redraw this. RT is 33.3. Now, that's kind of hard to grasp why that, if that makes sense, but let's think about this for a second. Imagine that this resistor was not in the circuit, okay? And we just had this. So what would the total resistance be right here?
50.
50, all right? So here's my current path. If I give current another way to go, will current go up?
No, it's going to be spread apart.
The total current.
No.
It won't be, okay? Well, let's think about this for just a second, okay? Say I've got my pump right here, right? Or actually, let's do this. Let's say we've got a water tank, and it's got a hole in it right here, okay? And I fill it up with water. And the water's gonna be running out, right? The water running out is my current, okay? Am I gonna have more water running out if I add another spigot right here?
No.
No?
Well, the same amount of water, it just run out quicker, right?
Yeah, but I mean, the
Yeah,
current,
yeah.
other than added together, it's gonna be twice as much, right?
Right.
It's gonna run out faster. What about if the spigot is just really small? Am I gonna have more current with both of these rather than just the one?
Yeah.
Yes, okay. So in this case, current can go pretty quick right here, can't go as quick here. But I'm adding more current right here, right?
Yeah.
So that means my total current would go up.
Right.
Does that make sense? A little bit? All right, hold on a minute. Let's try another way. Let me explain it like this. We've got our pump. It's got the 50 PSI of pressure, all right? And it's sucking water out of the tank, okay? And it's just shooting it back in. All right? So water's coming out. And the flow of the water, that's our current, right? My pressure is here. Now, my resistance is how small this pipe is,
Yep.
okay? I'll just say right there. That's our resistance. If I added another spigot right here, would more water come out?
Yeah.
The pressure's still staying the same, still gonna be 50 PSI up here.
Right, but it would be more water.
More water would come out, so that means if more water's coming out,
Then
the current is going up, right?
Makes
Because it's
sense.
pulling it,
Yep.
all right? Even if it's smaller, it doesn't matter, it's more current. So our original rules, current goes up, what does resistance do?
Go up.
If current goes up, resistance goes down. If we've got another path for current to flow, then it's gonna go faster, okay?
So the
If current went up, then resistance would have had to go down, okay? And that's why we have given current another path to flow. There is still 50 volts of potential right here, here, and here, right? And 0 down here. So if we give it another path, then it's gonna go faster,
Yeah.
all right? Okay, so parallel is kind of opposite of series. Here's another rule for parallel circuits. In series circuits, what's the same throughout the circuit?
Current.
Okay. And voltage is different throughout the current, or the circuit.
Yes.
In a parallel circuit, voltage is the same throughout the circuit. I've got 50 volts here, I got 50 volts here, and I got 50 volts here, right? Everything down here is 0. Correct? What do you think is going to be different?
Current.
The current. Which one of these branches is going to have more current flow in it?
First one.
The first one, because the resistance is lower, right?
Right.
So, and also, guess what? The current of this branch and the current of this branch added together is going to equal what?
Current of,
Total.
yep.
All right. So let's do, we know our resistance total, okay? When we know our voltage, so let's calculate our total current. What's our total current going to be? Remember, V is over I R. So we're looking for current, we cover up I, voltage divided by resistance. So that's 50 divided by 33.3.
Would be 150 milliamps.
150 milliamp? Is that what you got, Luke?
Yeah, pretty sure.
50 divided by 33,
Gives 1.50.
so it'd be 1.5 amp.
Okay, yeah.
1.5 amps, okay?
Yeah, that's right.
So IT is 1.5 amps. I don't know what happened right there. We got some highlighter there. All right. So now that I know the total current, how are we going to calculate the current in this branch? What do we know about this branch right here?
The
We know the resistance, and guess what else we know?
voltage.
We remember voltage is the difference of potential. If we measure the voltage here, it's 50.
Right.
So that means there's 50 volts across it,
Yep.
and there's 50 ohms, so we can calculate the current. What's the current in this circuit right here, on this branch?
1.
1. So what do you think the current's gonna be in this one?
Ooh, how, 0.
No.
No.
Two, you double.
Yeah.
Nope.
0.5.
Resistance went up.
Yeah.
Resistance went up, so we got 1 amp here, 0.5 here. Look, my current, so what's my current gonna be right here?
1.5.
1.5. All right. What's my current gonna be right here?
0.5. No. 0. No. Maybe 0.
1.5.
1.5.
Oh yeah. Yeah. I got you. Shit.
Because look, I've got 1.5 amps of current flow right here, okay? I think my finger's highlighting. I've got 1.5 amps of current flow right here. When it gets right here, 1 amp goes this way and 0.5 amp goes this way.
That makes
And then they come back together in 1.5, okay? Because there's just one path right here, but right here's 2 paths. How much current do I got right here at this point?
1.5.
0.5. What about this one?
0.5.
0.5.
Yeah. Makes
Okay.
sense.
See that? So, I've got an amp of current flow, and just because I added another resistor, doesn't mean that my current or my resistance is gonna go up. Because I've added another branch. I showed you, I touched base briefly on how to calculate the total resistance. Let's do 300, 600 ohms, 1.2K ohms, and then 300 ohms. Okay. Now, I told you, and our volts will go 75. Now, I told you total to find RT is R1 product over sum, right? So R1 times R2, that's our product, divided by R1 plus R2. That's our sum. But we've got an issue. We've got a third resistor here, okay? So there's 2 ways to do this. This is the way I do it, and I'm gonna show you that way. I'm gonna show you another way that you can do it as well, okay? People have their own preference. But first, you're gonna do R1 and R2 together. So that's gonna be 600 times 1200.
18.
600
Oh,
times 1200
7.
over 600 plus 1200. So what is 600 times 1200?
720,000.
720,000. All right, and then 600 plus 1200 would be 1800.
It's 400.
Huh? 400. And we know that's right because our rule stands. It's lower than those 2 resistors, right? 400. So the total, if I had one resistor here that was equal to 400 instead of these 2, that would be pretty much the same thing, right?
Right.
400 ohms, okay? That's the total of these 2.
So then to find since the third one's in there, we just do R2 times R3?
No.
Nope.
We take the total of them 2,
Oh.
which is 400 times 300. 400 plus 300. So 400 times 300 is what?
120,000.
120K over 700. What's that equal to?
171.4.
So RT 171.4, right?
Yep.
Alright. That's the way I do it, okay? I'm gonna show you another one. It's called the 1/1 method. And some people like using this way because it's calculator friendly, okay? So 1 is divided by 1/R1. I think it's plus.
It is.
Is it?
I think so.
Plus 1/R2 plus 1/R3. 1 divided by, well, I'll tell you what, what's 1 divided by 600? That's the first one, right? So this will be 600. And then R2 is gonna be 1200. And R3 is 300. So what's 1 divided by 600?
0.0016.
0.0016, all right, plus 1 divided by 1200,
0.0008.
0.0008, plus what's 1 divided by 300?
0.003.
Okay, so add that up, that would be
0.0057.
0.0057. 1 divided by 0.0057.
175.43. How did that equal 0.0057? 0.016 I mean, 0.008
That sounds about right.
Okay.
0.0054. Oh, 54.
5.4.
Sorry.
That, no.
I had the wrong number.
5.4, so 1 divided by 0.0054.
Is 185.18.
We've done something wrong. Should be right here or close to this. And it might be, it just might be off a little bit because of rounding that we, it probably is because we've done some rounding here, right? And that's probably why it's off, but it's relatively close to that, okay?
Still less.
All right, either way, you're gonna get close enough results from it, okay? So you can use either method, neither method is wrong, okay?
I like the first one.
I do too. That's why I show you what I do. I show you that there's other options that you can use because some people do the other way.
Correct.
Doesn't matter, okay? All right, so now that we know the total resistance, we can calculate what?
Our current.
Total current. What's the total current?
Uh, 43. No.
Be 75 divided by 171.4.
0.437. which is-
0.437, so it's 437 million,
Yeah.
okay? 0.437.
Hard time with the
So it's
decimal thing.
0.437 amps or 437 million. Same thing, right? Same thing. Okay. So that means I've got, at this point right here, I've got 437 millions, right? Right here. And right here, I've got 437 millions. Agreed?
Yep.
But it's gonna change here and here, these points, right? Because it's branched off.
Yep.
But we know the addition of these 3 branches will add up to 437 millions. So, let's do this. What is my voltage across R1? 75. What about R2?
75.
75. Voltage is the same throughout the circuit, okay? So if I know the voltage and the resistance across each branch. So what I want is the current in each branch. 1, 2, 3. R3, R2, R1. Tell me.
Minus 125 milliamps.
125. Okay.
Mine is 62 milliamps.
62, okay, sounds about right. Nick?
Mine's 250 million.
250, okay. Add them together. Hmm?
37.
437 million, okay? So how much current do I got right here? Do you think? Right here. Well, hold on a minute, hold on. How much current do I got right here? $250.
Yeah, 250, yeah.
Because this is part of the last branch, right?
Yep.
Now, I'm adding this one in right here, right? So how much do I got right here?
50 plus 312.
312. Because it's 250 plus 62, because this branch is added to it, right? 312. And then 312 plus 125,
437.
4037 right there for my total, okay? That's cool. Now, power is the same as in series circuits. Voltage times current, voltage times current, voltage times current, voltage times current, okay? If I'm looking for the power of resistor 1, I take the voltage of resistor 1 times the current of resistor 1. 2 and 3, same way. It's the same as series circuits. Does this make sense? Y'all want to go, and actually I did this on purpose, we can build this one right here out there and do like we did last time.
Yeah.
Let's do that.
What is the world? Okay, so we've got our circuit, and the first thing we gotta do is set the voltage, right? So we'll set it up on volts, DC. Okay, I'm going to turn the power on, and I'm going to adjust it to 75. Where's that? All right. So now that I've got that, I want to measure the total current, which we said the total current was going to be 437 milliamps. Okay. So what I'm going to do is I'm just going to take this neutral out right here and use my meter to connect it. Okay. Take my meter, I'm going to put this on amps. Amps DC. Turn it on. 425, so pretty close. Yeah. Okay. All right. Now, we know my voltage is going to be, because it's the same potential all the way across. This is my hot, 75, and this is my zero. So we know the voltage is the same across every one of them, right? Now, one thing I do want to show you, if I need some leads. Put this on the amps, and I'll just hold it like this right here. So I just want to measure the current of, let's not do this one first. Let's just do R1. So the current in R1 was going to be what? What we write down? 125 milliamps. Okay. So I'm going to take this, turn this on, measure the current in R1. Look at that.
Right on.
Okay. Put this back without shocking myself. Okay. And then I'm going to take
62.
62. See that? And then the current is 2,
250, I think.
somewhere around there.
Yep.
238. Okay. So also I want to show you too. Let me take this back out so I can measure the total current. And I'm going to show you how taking these resistors out of the circuit. So if I turn the switches, this is measuring the total current, 424. If I take this resistor out of the circuit, that's taking that 600 ohm resistor out of the circuit. What do you think current's gonna do, go up or down?
Go up. No, it's gonna go down.
It's gonna go down because we took
Yeah.
away a current path, right?
I gotta get that.
Okay, turn it back on. What about this one? This one's gonna, is it gonna make a bigger change or a, we know it's always gonna go down because we're taking a path out. But this one's 1200 ohms, so is it gonna make a bigger change or a smaller change? And
A bigger one.
it's gonna make a bigger change?
Double.
You sure?
Yeah.
Because there's not as much current on this one because the resistance is higher. So it's actually gonna be half of the change of that first one because it's 600.
Okay, that makes sense, cause,
Okay.
yeah, I was wondering how 3 or
And then this
600
one,
ohms.
It's gonna make the biggest change because it's got the lowest resistor in it, lowest resistance.